In this video, we're going to talk about how to use Thevenins theorem to calculate the current that is flowing through the load resistor, RL. So what we need to do is we need to determine the Thevenin resistance and the Thevenin voltage. Once we do that, we could simplify the circuit like this. Here is the load resistor, this is the Thevenin resistance, and this is the Thevenin voltage. And in this form, it will be relatively easy to calculate the current flowing through the load resistor. So let's find the Thevenin resistance first. So what we need to do is redraw the circuit. We're going to replace the independent voltage source with a short circuit. The independent current source will be replaced with an open circuit, so we're not going to draw anything there. And we're going to draw what is left over from point A to point B. So we're going to take out the load resistor. What we need to do is calculate the equivalent resistance of this circuit from points A and points B. Now, notice that the 4 ohm resistor is in parallel to the 5 ohm resistor. So the equivalent resistance of those two resistors will be 1 over 4 plus 1 over 5 raised to the minus 1. Now, these two resistors are in series with the 9 ohm resistor. So we can add 9. If you want to, you can redraw the circuit like this. This can help you to see it better. So this is point A, and this is point B. So here's the 9 ohm resistor, this is the 4, and this one's the 5. So now you can see that these two are parallel to each other, but in series with the 9. So the Thevenin resistance is going to be you should get 11.2 repeating. So that's the Thevenin resistance. Our next step is to calculate the Thevenin voltage. So what I'm going to do now is get rid of the load resistor, because what we need here is an open circuit. To calculate the Thevenin voltage, you need to have everything except the load resistor. So what we need to do is calculate the voltage potential between points A and B. Now we're going to assign this potential 0 volts. So that's going to be the potential at point B. Let's call this new point, point C. Now because we have an open circuit here after we remove the load resistor, there's no current flowing through the 9 ohm resistor. If there's no current flowing through it, there is no voltage drop across the 9 ohm resistor, which means that VC is equivalent to VA. And since VB is 0, the Thevenin voltage will be equal to VA. So if we could find VC, then in this example, that's going to equal the Thevenin voltage. So we're going to use nodal analysis to get the job done. So let's focus on point C and the currents that are entering and leaving point C. So let's call this current 1. It's going into point C, so that's going to be a positive current. We'll call this current 2. That's flowing into the junction, and then I3 is leaving the junction. So according to Kirchhoff's current law, the sum of the currents flowing in and out of a junction is going to add up to 1. So we have positive I1 plus I2 minus I3, and that's going to equal 0. Now, we know that the current is equal to the voltage divided by the resistance based on Ohm's law. So to calculate I1, the voltage across this resistor is going to be 50 volts minus the potential at point C divided by the 4 ohm resistor. I2 is based on the current source of 3 amps. I3, now there's no current flowing through the 9 ohm resistor. So I3 is flowing completely through the 5 ohm resistor. So I3 is going to be the potential at C minus the potential at B, which is 0, divided by the 5 ohm resistor. Because I3, all of it flows through the 5 ohm resistor. So now we have this. We need to calculate or solve for VC. Let's multiply both sides by 20. So we're going to have 20 divided by 4, which is 5. And that's going to be multiplied by 50 minus VC. And then 20 times 3 is 60. And then 20 divided by 5 is 4 times what we see here. So that's going to be negative 4 VC. Now let's distribute 5 to 50 minus VC. So 5 times 50 is 250 minus 5 VC plus 60 minus 4 VC, which equals 0. 250 plus 60, that's 310. Negative 5 plus negative 4 is negative 9 VC. But if we move it to the other side, it's going to be positive 9 VC. Dividing both sides by 9, we get VC, which equals the Thevenin voltage, and that's going to be 310 divided by 9, which is 34.4 repeating. So that's the Thevenin voltage for this problem. So now we can draw the simplified circuit. Which looks like this. So we have a Thevenin voltage of 34.4. We have a Thevenin resistance of 11.2 and a load resistance of 6 ohms, which was what I wrote down before. So now we can calculate the current flowing through the load resistance. So that current is going to be the voltage divided by these two resistors in series. The voltage is 34.4 repeating, and the resistance is going to be 11.2 repeating plus 6. So that's 34.4 repeating over 17.2 repeating, which gives us a current of 2 amps. So that is the current flowing through the load resistor. Now we can confirm the answer by solving for everything in the circuit. So here is the circuit that I redrew, and we said that the current flowing through the 6 ohm resistor is 2 amps. So if this is the ground potential at 0 volts, 2 times 6 will give us a potential at point A, which will be 12 volts. And we said this is point C. Now we still have 2 amps of current flowing through the 9 ohm resistor. So 9 times 2 is 18. Add an 18 to 12 gives us a potential of 30 volts at point C. Now 30 divided by 5 is 6. So we have a current of 6 amps flowing through the 5 ohm resistor. Now let's think about this. So we got 2 amps flowing in this direction, 6 going here. That means that there must be 8 currents, not 8 currents, but 8 amps of current that is flowing in that direction. Now we have a current source of 3 amps flowing in this direction. So 8 minus 3 is 5, which indicates that 5 amps of current is flowing through the 4 ohm resistor. Now 5 times 4 is 20. So we have a voltage drop of 20. Add that to 30. That gives us the potential of 50 at this point. So we could see that everything makes sense, everything adds up. All the currents and the voltages, they follow, KVL and the KCL laws. So that's it for this problem.